Okay, everyone, welcome to the next screencast looking at single-dimensional spatial models, still in Chapter 5, still in what I call the first part of Chapter 5. This is getting toward the end, though. We're now going to use these models to discover something. We're going to use these models to generate one of the first findings in social choice theory, especially the first findings using spatial voting models. And it's something you may have heard of or heard referenced in other classes and other situations. It's something called the median voter theorem. And the idea we commonly hear is that kind of in politics, the person in the middle gets their way, all right? Or things tend to move toward the middle, all right? And we're going to see under what circumstances that's the case. And then when we move to two-dimensional models, we're going to see how it gets really different, okay? So, win sets and vote cycles. All right, alternatives with an empty win set, majority rule win set, are Condorcet winners. All right, so if an alternative has an empty majority rule win set, it is a Condorcet winner. When we see a vote cycle, like a Condorcet vote cycle, we know that it's a situation where no Condorcet winner exists. All right. In the language of win sets, that means there's no alternative in the space that has an empty win set. But remember, way back in an earlier screencast, we said that if we restrict universal domain, if we don't require that property of Arrow's theorem to hold, and say everyone must have, or we have a situation where everyone does have single-peak preferences, then we won't get a Condorcet vote cycle. We will always get a Condorcet winner. All right, so let's back that up. Alternatives with an empty win set are Condorcet winners. So if we have single-peak preferences, we're guaranteed a Condorcet winner. When we see a vote cycle like the Condorcet vote cycle, we know there is no Condorcet winner. So that's going to mean that we don't have single-peak preferences, or, as it turns out, the situation is not single-dimensional. All right? And that's where we're really going to get the wrinkle in the median voter theorem. But first, we need to run it down and get it down pat first, all right? So if we restrict the types of preferences that voters can have to single-peak preferences, then we will not have a cycle and we will have a Condorcet winner, which means there will be at least one alternative that has an empty win set, an empty majority rule win set, all right? So if voters have single-peak preferences, there must exist an alternative that has an empty majority rule win set. In short, single-peak preferences lead to a Condorcet winner in a single-dimensional model. We're still in the single-dimensional model section of the chapter. But spoiler alert, this bottom line here does not hold in multiple dimensions. All right? This is for a single-dimensional model that single-peak preferences give you a Condorcet winner. All right? So, we know there's going to be an alternative that has an empty win set. Which one is it? All right. As it turns out, the alternative that is the Condorcet winner is going to be the ideal point of the median voter in the space. That means the ideal point of the median voter has an empty win set. So this is going to kind of be a long example. And don't worry, whenever we go to actually work with these kinds of models, you're not going to have to go through all of the, 30 or 40 steps, I forget how many that I'm about to go through here. But I'm doing this so that you can see the internal logic of the median voter theorem without us having to do the mathematical proof, all right? We could go that way. We could do the mathematical proof of the median voter theorem. But even if we did, if you're like me, there wouldn't be a ton of intuition there. I mean, yes, you could see the proof, and if you could follow the math, you could say, yes, it is true, but it doesn't really help you understand what's going on intuitively. So I'm going to go through this elaborate example of the median voter theorem to demonstrate it so that you can see the internal logic of why there is a median voter theorem, all right, without doing the proof. So here's our set of voters: Frankie, Aaron, Anna, Florian, and Brittany. This is their ideal points. Frankie's ideal is 10. Aaron's is 25, Anna's is 30, Florian's is 40, and Brittany is at 70. Those are the points in the issue space that maximize their utility We have single-peaked symmetric preferences, so we don't need to draw a utility dimension. All that matters is the distance of an alternative from their ideal point. That is how we will judge their utility. All right. We're going to start here with the status quo policy at 20. So let's take a look at everybody's preferred two sets. All right. Here we go. I'm drawing in everybody's preferred two sets. Is that everybody? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. Frankie prefers everything between 0 and 20, not including 0 and 20. Brittany is way out here at 70. She prefers everything between 20 and 70. And she would prefer everything between 70 and I think 120. But that's out of the issue space. Off of the issue space. All right. She prefers everything between 20 and 80. But 80 is strictly preferred to 20. 80 is only 10 away. 20 is 50 away. She strictly prefers 80, so that's why we have the hard bracket. Anna prefers everything between 20 and 40, non-inclusive. Florian, everything between 20 and 60, non-inclusive. And Aaron, everything between 20 and 30, non-inclusive. So here are everyone's preferred two sets. So they draw a name out of a hat, and Brittany gets to propose something first. All right. So what should Brittany propose? Well, Brittany's ideal point is 70. So should Brittany propose 70? Oh, by the way, I forgot to mention they are using pairwise majority rule. They're going to propose something to face the status quo. They're going to vote. The thing that gets a majority wins. Okay. Brittany knows that. She knows where everybody's location is. There's full information in these models. All right, complete information, full information. So Brittany might think, well, should she propose 70? She's going to get to propose an alternative to face the status quo. All right, and like I said, they all have full information. So she can deduce the win set here. All right, she can figure out what would pass and what would not pass. And she knows she's kind of an extremist here. She's way out here. So she might already intuitively know, if I propose 70, a bunch of these guys aren't going to like 70 better than 20. So maybe that's not my go-to here. Maybe I want to propose something that is as close to my ideal as I can get, but that will actually beat 20. So let's find the win set. How many voters are needed? We have 5 voters. Divided by 2, we get 2.5. Round up to the nearest integer. Right? I put that on a slide in the last screencast. So this group needs 3 people to vote yes to defeat a status quo. So what we are looking for when we're going to find the win set is the set of alternatives that at least 3 people prefer. 4 can prefer it, 5 can prefer it. But the majority rule win set is the set of alternatives that at least 3 people prefer. All right? So where is the set of alternatives that at least 3 voters prefer to status quo 1? Where at least 3 preferred two sets overlap. Here, 4 overlap. Here, 3 overlap. Here, only 2 overlap. And here, there's no overlap. So somewhere in here is the set of alternatives where 3 preferred two sets overlap. Starting here, 4 overlap. So all of these are good, right? All the way up to here, we have 4 against 1. If we go past Aaron's 30, we still have 3 that overlap. And if we keep moving, okay, here is where we move. If we keep going, only 2 people prefer two sets overlap. So the set of alternatives that at least 3 people prefer to the status quo, aka the majority rule win set of the status quo, is everything between 20 and 40, non-inclusive. It often will correspond with at least one voter's preferred to set. It doesn't always have to, but it often will. All right. So this is the preferred to set of the status quo. The win set of the status quo of 20 is everything between 20 and 40, but not including 20 and 40. 20 and 40 are on Anna's indifference points, So we don't know exactly what she would do in that situation, all right? We want to know the things that will strictly beat 20, and that is here, the win set. Okay, so what should Brittany do then? All right? Well, if she's being strategic, she's not going to propose 70. 70 will not pass. It is not in the win set. It will not win. 60, not in the win set. It's better than 20 for her, but it's not going to pass. So she wants to propose the closest thing to her ideal point of 70 that is in the win set. So she wants to propose like 39.9 repeating, right? That will pass, all right? So she proposes 39.99. All right, I probably should have said 99 repeating, but you get the idea, all right? And it will pass. It is in the win set. By definition, it will win, and it will become the new status quo, 39.99 repeating. Now let's draw everyone's preferred two sets again. All right, 1, 2, 3, 4, 5. So the preferred two set of this status quo 2, 39.99 for Frankie, is everything between his ideal and the status quo, and it would be symmetric the other direction, but we run out of issue space. So 0 is in the preferred two set, 39.99 is the boundary of his preferred two set, and we do that again for all 5 of the voters. I'm not going to go through that in detail again, because this being a screencast, you can always go back and rewatch the screencast on preferred two sets if you don't see where some of these come from. That'll let me speed up here just a little bit. All right, so here are all the preferred two sets, and now we're going to draw a name out of the hat again. Well, first let's find the win set. So the win set is everywhere that at least 3 people's preferred two sets overlap. Notice everything on this side of 39.99 only has 2 people who prefer it, and really only for a little bit. Really, it's only Brittany, way out here, who prefers a lot of the things that are above 39.99. Florian has this tiny preferred two set, all right? So over here, it looks like we have a set of alternatives that at least 3 prefer, going from 39.99 all the way to 20.1, all right? And it's Anna's preferred two set, all right, in this situation. So the win set, the majority rule win set of the status quo 2 is everything from 20.01 to 39.99, not including those 2 boundaries, all right? So let's say we draw a name out of the hat, and this time it's Frankie. So Brittany went already. So we're going to hold her name out until everybody gets to go, and then we'll throw all the names back in the hat again, all right? So Frankie goes, what should Frankie propose? Frankie, you might think, hey, 10 would be great, but 10 is not in the win set. 10 would fail. He would be wasting his turn, basically. If he proposed 10, it would be defeated, all right? Aaron would not even vote for 10. He's the only person who would vote for 10, all right? So he wants to propose the closest thing to his ideal point that is in the win set. The win set is from 20.01 to 39.99, so he wants to propose the closest thing possible, all right? So what will Frankie propose? He will propose 20.02, all right? That's the closest thing to his ideal that will pass. It wins because it is in the win set, and it will become the new status quo, all right? Status quo 3, all right? So I've already gone through quickly and drawn out all of the new preferred two sets. I'm going a little more quickly here. So these are the preferred two sets for 20. Now remember, you're not going to have to do all of these steps when you want to use the median voter theorem. This just keeps us from having to do the proof, right? Because we're going to get the intuition of why the median voter theorem holds from walking through this, all right? So here are all the preferred two sets. The majority rule win set is where at least 3 people's preferred two sets overlap. Looks like, again, it's going to be Anna's preferred two set here is going to be the win set of the status quo, which is 20.02, all right? So we already had that win set more or less, not exactly, but pretty close. Are we in a cycle? We're not in a cycle, All right, we're not in a cycle. A cycle is where you come back to the same alternative that you got before, and it keeps going round and round. All right, we're not in a cycle. So now we draw Anna's name out of a hat to propose. So Anna wants to propose the closest thing to her ideal point that is in the win set. Anna's in luck. Anna's the first one to get lucky because her ideal point is in the win set. Anna's ideal point is 30. 30 is in the win set of this third status quo in these rounds of voting. Oh, some thunder. Let's hope my power doesn't cut out here while I'm filming this. This happened to me earlier and I had to redo all of this. All right, fingers crossed. So Anna is going to propose her ideal point. It's in the win set. It will pass. Hooray for Anna. She's going to get her ideal point. But will it hold? Will someone just propose something else that will beat it? Let's see. So Anna proposes 30 and it wins 3-2 because 3 people prefer it, 2 people don't. It passes. All right. So let's now draw everyone's preferred to set again. Here's Frankie's, here's Brittany's, here's Anna's, here's Florian's, here's Aaron's. Notice Anna's preferred to set. Anna's preferred to set of 30 is empty set. There is nothing Anna prefers to 30. It is her ideal point. It maximizes her utility. It is the peak of her utility function. If we were drawing utility functions onto the vertical dimension. So Anna's preferred to set is empty set. So let's now find the win set, the majority rule win set. We need the place where 3 people's win sets overlap. Okay. Nothing over here. Only 2 people's win set overlap between 0 and 30. Nothing over here. Only 2 people's win sets overlap between 30 and 80. Again, non-inclusive of 30. There's nowhere that at least 3 people's preferred to sets overlap. So the win set here is empty set. All right, the win set is empty set. Anna does not have a preferred to set. So notice we've pulled one person out, so she isn't going to vote with this side and she isn't going to vote with this side. All right, this is the logic of the median voter theorem and why the ideal point of the median voter cannot be defeated in pairwise majority rule. The person who is at the median, and how do I know she's the median? Well, I have 1, 2, 3, 4, 5 people. So to find the median, we just start tossing people out. So toss Frankie, toss Brittany. Toss Aaron, toss Florian. Here's Anna in the middle. She's the median voter. All right. She's not going to vote with either side. So if the status quo gets to her ideal point, or her ideal point becomes the status quo, might be a better way to say it, then nothing can happen because nothing can beat it in pairwise majority rule because she always has to be a part of the majority because she's in the middle. All right. So there is no majority rule win set at her ideal point. It is empty set, and it cannot be defeated in pairwise majority rule. It is a Condorcet winner. All right? And I just said all this. Yep, I don't know why we need the animation. So this is the median voter theorem. The median voter theorem says, this is Black, was the first guy to come up with this. It was popularized by Anthony Downs in a Economic Theory of Democracy was the name of the book. So here's how it's stated. If members of a group G have single-peaked preferences, then the ideal point of the median voter has an empty win set. And we should add here, if there is only one issue to mention, and again, this is within the context of the first part of the chapter, which is strictly dealing with single-dimensional models. This goes out the window with two-dimensional models. I've already spoiled that, surprise. But if the issue space is single-dimensional and everyone has single-peaked preferences, the ideal point of the median voter has an empty win set and therefore cannot be defeated in pairwise majority rule. Therefore, it is a Condorcet winner. All right? I think a better way to say it is this. If members of a group G have complete, transitive, reflexive, and single-peaked preferences, okay, complete, transitive, reflexive, should be a comma there, sorry. Those are just our assumptions of rationality. Right? So if they're rational by our definition, single-peaked, we need, right? Single-peaked preferences, we need that to get this median voter theorem. Notice symmetric is not in here. We don't need symmetric preferences for the median voter theorem to hold. We used them in our example because it makes the math easier. Trust me, we don't really want to do the proof that allows for asymmetric preferences, but it does hold. So if members of a group have complete, transitive, reflexive, aka rational preferences, and single-peaked preferences, and the issue space is single-dimensional, I just mentioned that, this holds for single-dimensional issue models. So it has to be plausible that what we're considering, everyone basically considers it on a continuum, the same continuum, from 0 to whatever, all right? If those things hold, then the ideal point of the median voter cannot be defeated in pairwise majority rule, all right? That is the median voter theorem. So now let's drop back. I want to talk about one more thing. I want to talk about the unanimity rule win sets, all right? I'm just going to do it for the 3-person example. Okay, so here's an example back with 3 people. And we already found the majority rule win set for this in the previous screencast. We said that the majority rule win set was where you take the number of voters, divide by 2, so 3 divided by 2 is 1.5. Then you round up to the next integer, which is 2. So it's everywhere that at least 2 members' preferences overlap. And so the majority rule win set here was between 40 and 60. But there are other win sets. For example, where is the unanimity rule win set? Unanimity rule is the set of alternatives that would beat the status quo using unanimity rule. Unanimity rule requires everyone to prefer the alternative to the status quo. So for unanimity rule, you need everyone's preferred 2 sets to overlap. This status quo has no unanimity rule win set. All right? There is no place where all 3 voters' preferred 2 sets overlap. So let's look at one more unanimity rule example. Again, the same 3 people, same ideal points, but I've put the status quo here at 10%. So I first draw all their preferred 2 sets. Carrie prefers everything between 10 and 20, and everything symmetric from 20 to 30 on the other side. She has single peak symmetric preferences. Adam prefers everything between 10 and his ideal point of 50, and then symmetrically going 40 in the other direction. Helen prefers everything between her ideal point and 10, and then she would symmetrically in the other direction, but we run out of space, so that's her preferred 2 set. The unanimity rule win set for this group is where everyone's preferred 2 sets overlap. In this case, there is an area that does that, right? Everything between 10% and 30%, everyone prefers to the status quo. So the unanimity rule win set of this example for 10% is everything between 10% and 30%, not inclusive. Okay, that's it for this one. We're going to go multidimensional next time.